Welcome viewers to the 13th lecture of the course non-traditional machining methods with the help of abrasives, and today we are going to take up some of the numerical problems in abrasive jet machining. We have already done a number of problems in that field, and we will also discuss some aspects of the machine configuration, the different modules in the machine which are essential for the abrasive for the abrasive jet, and if possible some MCQs as well. This is on volume flow ratio and mass flow ratio. Please remember, we are talking about volume flow ratios and mass flow ratios. During EJM, ratio of volume flow rates of abrasive and gas is 0.2. So, that means volume flow rate of abrasive particle divided by volume flow rate of carrier gas is equal to 0.2. Now, calculate ratio of mass flow rate of abrasive to the combined mass flow rate of abrasive and gas. Okay? If the ratio of density of abrasives to the density of carrier gas is equal to 20. So, this seems to be quite simple, only we have to be alert that we do not make any wrong assumption. So, given volume flow ratio has been given to be 0.2 and we have formally defined it. Volume flow rate of abrasive particle divided by volume flow rate of carrier gas. Next, so that is V dot A by V dot G. Now, mass flow rate of abrasive to total jet mass flow rate is equal to abrasive mass flow rate, which is M dot A, by combined mass flow rate of abrasive and carrier gas, which is M dot A plus G, let us say. So, if the volume flow rate is 0.2, alpha, which is mass flow ratio, it is equal to rho G into rho A into V dot A divided by rho in A into V dot A plus rho G into V dot G equal to, we are dividing through, okay, we are dividing through by, rather we are putting in the values of the density ratio. What is density ratio? Density ratio means abrasives are much more dense than the carrier gas, and therefore, density of abrasive by density of carrier gas is 20. So, let us divide the whole equation here by density of carrier gas. So, we will have here in the numerator we will have rho A divided by rho G, and here also we will have rho A divided by rho G, and therefore, we will have here 1 into V dot G. So, rho A by rho G value we put in as 20, and therefore, that is why we have 20 into V dot A plus 20 into V dot A plus 1 into V dot G, and therefore, this becomes 20 into 0.2, which is 4, and 20 into 0.2 plus 1, which is 5, and therefore, this mass flow ratio is 0.8. Mass flow ratio is 0.8. Therefore, we have found out effectively the mass flow ratio, which is defined as abrasive mass flow rate divided by combined mass flow rate of abrasive and carrier gas. Okay. Let us move on to the next one. So, now after all those numerical values, we have now a good understanding of what is going on at a mathematical level, but up till now we have not seen the different parts of the EJM setup. This is the EJM machine setup, and let us have a quick look at the essential equipment which have to be provided. Okay. So, first of all, there is a gas cylinder. From this gas cylinder, we are going to have a supply of gas at high pressure, and the pressure relief valve will ensure that you are going to get whatever pressure you set the machine to. Okay. Do we always have to work with a gas cylinder? No. We can have a compressor, and however, whether it is a gas cylinder or whether it is a compressor, we have to make sure that this particular air is first of all completely free of any moisture, and it is completely free of dust particles. Why is moisture going to create a problem? This is because even if there is a trace of water vapor present in the gas, once it is present, it can ultimately give rise to agglomeration and clogging. Agglomeration means that if there are abrasive particles of size to the tune of 10 microns to 50 microns, okay, they will have a tendency to agglomerate. That means come in contact with each other and get stuck with each other, and at the micro level it is extremely hard to separate them from each other. But what is the problem if they are agglomerated? The problem is that this particular nozzle diameter that we notice here, it is from 0.2 to 0.8 microns. Why is it very small, small in diameter? That is because if the diameter is small, the jet of abrasives which will be emanating from the nozzle, that will have a jet diameter limited to say 0.3 to 0.9 millimeters, and therefore it itself will be able to give rise to a very narrow cut or groove or diameter of drill, like that. So, we cannot have a large outlet diameter of the nozzle, and therefore we cannot have agglomeration of the abrasive particles which are 10 to 15 microns in diameter. Moreover, when the air is entering the mixing chamber, it might be entering with a still small diameter, but that is a different story altogether, because at that time it is not mixed up with abrasives. So, first of all, there is a drying chamber through which the air has to pass, air or nitrogen, etc. We will discuss that later on. Whatever is the carrier gas type, when it has to pass, in that case, if it has to go to the mixing chamber, first of all it is dried so that the water vapor is removed, and it is filtered so that dust, dirt, etc., all these things, dust and dirt, will be first removed from the air. The air is still at very high pressure, and it enters a chamber called mixing chamber. What is this mixing chamber for? The mixing chamber is the particular place where abrasives are going to be injected into the air line. Now, what is so special about that? The specialty is this, that air being still at a very high pressure up till say this point, if we introduce abrasives into it, the high pressure air will not allow the abrasives to enter. It is like if you try to put in the abrasives through a particular, say you make a hole and you are pouring the abrasives just like pouring from a say bottle, and immediately you will find that the mixing chamber will push them out. It will push them out, and maybe it will go to your face if you are nearby. You have to be very careful. So, we have to have a method by which the abrasive particles can be made to enter inside the mixing chamber. Now, how can that be done? That can be done by the principle of the jet pump, where the air is made to enter this chamber with a very small diameter. Okay, the exit diameter here is a very small diameter, and the air comes in, it fills up this particular mixing chamber, and then it goes out to be finally, finally get emitted to the open atmosphere. So here there you have atmospheric pressure. So it will have a particular output velocity. Here what happens is, as the air is coming out through a very small diameter and expanding here, the pressure energy gets converted to kinetic energy, so it develops a definite velocity, a very high velocity. Here the velocity with which the abrasives come out, which it will be a little lower, because this velocity is coming out defined by as defined by this particular diameter, and also this velocity due to continuity conditions. If this diameter is slightly higher, it has to be between 0.2 and 0.8, and therefore you will have a negative pressure being created here, which will suck in the abrasives through this hopper. Okay, the abrasives get entrained into the air, because here there is a very small diameter entry and there is a slightly higher diameter here, so that vacuum pressure is created. Okay, so these abrasives get entrained and they travel together, get accelerated to the velocity of the final jet, and it is emitted at this particular place. Okay, so there are other ways of putting the abrasive into the chamber. For example, you can have a back pressure line. That means from the cylinder itself you can have a line of air, a pipe of air feeding in at the back side of the hopper with a higher pressure than this one, so that it will drive the air inside. So, and there is also a shaker which vibrates the mixing chamber, so that the mixing of the abrasives and the air, it is made easier. After that, the air and abrasive mixture, they go down the line and ultimately get emitted at the exit of the nozzle. So let us have a quick look at the different aspects of this particular machine. So sometimes what happens is, AGM is literally equated to sand blasting, but sand blasting and AGM, they are not the same. Sand blasting, rather AGM, is much more refined and it is a much more controlled process. The abrasives which are used, they are carefully selected and controlled, and it is applicable not mainly, it is applicable to finishing work as well as machining operations like cutting, grooving, drilling, etc. With sandblasting, we cannot do cutting, grooving, etc. And advantages which are which can be mentioned, they are the first is advantages can be mentioned as, say, inherent cooling mechanism in the system. Okay, the air jet which is coming out, which it has automatic cooling mechanism incorporated in the particular process, and it is also able to machine fragile heat sensitive components and cut out intricate patterns on brittle sheet like materials, which is not possible by other beams. Okay. So, these advantages make it possible for us to use AGM in special applications, and sand blasting is absolutely not comparable with this particular process in these respects. Further, finishing operations like so these are machining operations, and it can also do finishing operations like deburring, trimming, deflashing, cleaning of internal passageways, forming on rough edges, and removing rough surfaces on castings, etc. We will definitely list and study the advantages at a later stage. So, supply of gas. So, gas can be supplied from cylinder or compressor, and the gases can be air, argon, nitrogen, carbon dioxide, but not generally oxygen, because oxygen may create a condition of sort of burning and fire hazard and other things can occur. And what will be the pressure like? The pressure can be typically 5 kg per centimeter square is good enough a pressure for creating a reasonably high velocity of gas jet. And as we have discussed, the air or gas needs to be dried, or else the water content causes agglomeration and clogging. And agglomeration and clogging we have already discussed, so we already know about that. And the gas needs to be free of dust particles, as to reduce contamination. And in order to introduce abrasive particles into the gas stream, we have already discussed this point also. The nozzle. The nozzle is one of the most important parts of the equipment, and the nozzle is generally made of very hard, wear resistant materials like tungsten carbide or sapphire. Okay. So, why so? Because all the abrasive particles are getting, they are flowing down the internal passage inside the nozzle, and unless these are highly wear resistant, they will ultimately be of no use after, say, a few hours of service, say 10 to 20 hours of service for tungsten carbide, and somewhat more hours of service for sapphire. And about the mixing chamber, we have already discussed it. This is the figure of the mixing chamber. Gas is coming in at high pressure, and inside the mixing chamber abrasives are coming through the hopper, and they are getting entrained here. At the end of the hopper there might be a sieve, okay, a sieve through which the abrasives can pass, and this whole thing might be mounted on a vibrating chamber, so that the abrasive feeding becomes easier. Let us discuss some of the applications of AJM. We can have not only cutting, drilling and grooving and other things, but we can also have use the abrasion or the abrading action of abrasives to create frosted glass appearance. So, if we are having, say, a glass in which we need a frosted glass appearance, apart from other methods which might be existing, abrasive jet machining is definitely capable of doing it. Okay. It can also produce some matte finish by using special kind of abrasive particles like aluminium oxide, etc., dolomite. They can give matte finish, frosted glass appearance, etc. So, this can be done on glasses, ceramics, refractories, etc. Then it can be used for cleaning purpose also, cleaning of, say, metallic smears on ceramics, etc. Then oxide layers can be cleaned out, and resistive coatings which have been put, which have to be removed, they can also be done by abrasive jet machining. The manufacture of electronic devices, deflashing and trimming of parting lines. Whenever there is injection molding or casting, etc., deflashing, the flash of material which comes out, that can be removed by AJM, and parting lines can also be trimmed from castings and molds, I mean injection molded material, and engraving can be done on toughened glass, microfabrication can be done, and then we have a list of materials on which the regular machining operations can be done, like cutting, drilling, grooving. What are these? Glass, quartz, sapphire, mica. So all of these are essentially either hard and what do you call it, hard and brittle materials, then wear resistant materials, and they might be glasses, ceramics, then semiconductors. So you have mica, sapphire, ceramics, germanium, that means semiconductors, silicon, gallium, etc. We can also carry out the deburring of milled parts. That means after we have done milling, or if we have made small holes, etc., they might be having some material sticking to their surfaces, which is called which has to be removed very carefully, and two of these processes can be deburring first of all, and also putting the abrasive jet into inaccessible places like inside small holes or inside some pipes, internal passageways, etc., small holes in hypodermic needles, etc., where cleaning and deburring can be performed, which is not possible by other processes. Okay. So this way we come to the end of the discussion in the 13th lecture. In the next lectures, we will take the remaining aspects of abrasive jet machining and move over to abrasive water jet machining. But before that, we will also have a session on multiple choice questions, which are ultimately the forms of questions that you have to answer. Thank you.